Swayam Prabha. Digital India. Educated India.
Okay, so for each x, I can go and ask, is this property true for that x? So what is this property saying? There is some y such that x likes y. So x likes somebody. Okay, so I'm just going to make this new predicate, which just takes one input now. It's takes one input x here, and it tells you whether x likes someone or not. Okay, so just to fill it in, Alice does like someone. She likes two people, in fact. So indeed, at least there is at least one person that she likes them. And same with Jabberwock and Flamingo, they like themselves. So we already saw this statement is true, but here is kind of how to interpret this statement in terms of how we defined quantified expressions, right? So we were implicitly defining a new predicate. That x is y likes xy, this part of this proposition is a new predicate, and this is saying, for all x, that new predicate evaluates to true on x. All right, so that's all I wanted to say about it now, and you should work on exercises. But what I'm going to do in the rest of this clip is to give you take you through some manipulation of quantified propositions. Things can get a little tricky, though many things are fairly intuitive. So let's start with this. So I told you order of quantifiers is important, right? And that might have been a little non-intuitive. But here is a place where it's not important. So both the quantifiers here are universal quantifiers. So I have on the left for all x, for all y, p of xy. Okay, so this is just saying that if you listed all pairs x comma y, p of xy is true everywhere. So for all pairs xy, p of xy holds. And it doesn't matter if I write it as for all y, for all x, p of xy, it's saying the same thing. Okay, so here the order of quantifiers doesn't matter. And same thing with their x's. If I have two their x's back to back, the order doesn't matter. So in this case, both of the statements here are saying is that there is some pair xy such that p of xy holds. Right? There is some x you can pick such that there is some y you can pick such that p of xy is true. And if that is the case, yeah, so there is some pair xy such that p of xy holds. And you could have made the same statement by quantifying over y first. Okay, so that's, things are a little simpler when you have a run of the same type of quantifier. The difficulty is when you have alternating quantifiers, if you alternate between for all and their x's. Here's another kind of rewriting you might want to do. So on the left, I have a statement saying for all x, px or r. Okay, so my convention is, unless it's otherwise stated, when I just write for all x, px or r, the scope of x extends all the way to the end. Okay, so it's for all x, px of r. Until, of course, if the whole thing is inside a bracket or something. So if you encounter an unbalanced bracket, then the scope ends. But otherwise, the scope goes to the end. Okay. Okay. So what is the statement saying? For all x, px or r. Let's think in terms of a finite domain. So say it has elements a1, a2, a3, and so forth. So this is saying pa1 or r and pa2 or r all the way up to pan or r. Okay, so if there are n elements in the domain. So that is what the statement is. So sticking to that finite domain, let's see what the right hand side is saying. It is saying for all x px, so pa1 and pa2 and pa up to pan or r. Okay, and now if you remember the distributive property, this expression pa1 and all the way to pan or r expands to exactly this one, pa1 or r and all the way to pan or r. Okay, So this equivalence here is actually just the distributive property, distribution of R over and. Except, of course, is more general. It's meant to work for infinite domains also. So how do you know it actually works for infinite domains also? You will need to give a proof. We'll talk about proofs a little more elaborately later, but here is a quick proof for this particular statement. So here R, remember, is something that does not involve X, and this proposition can take only two values, okay? It can be either true or false. And what we are going to say is that so the equivalence here is saying no matter what the predicate P is, when you substitute all values of X and look at, when you evaluate this expression on the left and when you evaluate this expression on the right, you'll get the same truth value, right? And in evaluating this, you have to substitute R, that R either takes true or false. So we'll consider the two cases separately. Suppose R takes a value true. Then what is the left-hand side? It's just for all x px. So this for all x, px are true, right? But px are true is just px. So this becomes for all x px. What is the right-hand side? It says, for all x px are true. But, oh, sorry, this is an R. So I should say for all x px are true was actually true. Right? Px or true is always true. So for all x, px or true is just for all x true. And for all x true, value is to true. On the right hand side, it's for all x, px or true. And anything or true is true. So when R is true, both the sides evaluate to true. What about R is false? That's what I was earlier referring to. Px or false becomes Px, right? Or false doesn't change, you'll get whatever is the first one. So you'll get Px. So the left-hand side changes to for all x Px. The right-hand side becomes for all x Px or false, but this or false doesn't change anything. So this becomes just for all x Px. So both sides are the same for all x Px. So in all cases, these two sides are equivalent to each other. All right, so that's simple enough, and so no surprises in some sense. You can just take this for all, sorry, this or are outside, right, outside the quantified statement. And there's nothing special about or here. Same thing works with and as well. And there's nothing special about for all either. It works with their x's too. Okay, so all this is a distributive property, and or distributes over and distributes over or. So intuitively, it's all following from the distributive property. How about to change this or and to something a little more subtle, say implies. So for all x, R implies Px. Well, R implies Px is just saying not R or Px. So it's actually not very different from the statement here, right? This said R or Px. This is not R or Px. But, so with using not R instead of R and using this expression, you get this is equivalent to not R or for all x px, and that is the same as saying R implies for all x px, right? So this equivalence again, nothing delicate going on here. You can just take this R implies outside of the quantified expression and everything works. And similarly, it works for their x's also. Okay, you can verify yourself. But things get a little tricky if the implication, if it's Px implies R instead of R implies Px. Okay. Now you should try to think this through in English later, but the only sure way of making sure you're getting the logic right is to go about it mechanically. So let's see what this is. So Px implies R is simply not Px or R. Okay, and I put this underline to, emphasize that the scope goes to the end. So this is just, for all x, not Px or R. And now okay, we can apply one of these above statements. You can still take R outside. So this becomes for all x, not Px or R. But here is the thing, right? If you want to rewrite it back in terms of implies, you need negation of something. So you need to write this, you can rewrite this as negation of their x is Px, right? Remember from our equivalent of De Morgan's law here, their x is Px. If you negate, you get for all x not Px. So that is what this is, for all x not Px. So you can rewrite this as not their x is Px or R. And that is just saying their x is Px implies R. Okay, so this statement on the left here, saying for all x, if Px then R, is the same as saying if there is some x such that Px holds, then R. Okay, and I invite you to, come up with English sentences or scenarios where you can make sense of this. Okay, and here is something which maybe even it's exactly analogous to this, but again could be a little delicate to understand in English, right? So this is saying their x is x, Px, if Px then R, is the same as for all x Px, if for all x Px then R. And you should also, of course, try deriving this exactly following this template. Now, here is another kind of manipulation I want to show you. Here are two statements for all x Px and for all x Qx, and I combine them using a conjunction. Okay. So what is this saying? You look at, we are looking at two predicates, P and Q. And here is my domain. And the first statement on the left is saying for all x Px holds. Okay, so this is kind of lit up in every cell in that column. And for all x Qx. Okay, so this is second column is also lit up. So basically it's just saying every cell here in both these columns taken together is true, which is what I mean by it's lit up. How about the right hand side statement? It says for all x, Px and Qx. So if I take the first x, I have Px and Qx both are true. But it's same thing for all x, right? So basically for all x, both the cells are lit up, which again says, taken together, it says this entire two columns and all these rows are lit up. Okay, so these two things are saying the same thing. They're equivalent statements. If you look at it, what happened in terms of the expression, we could just take the for all x outside and just have this Px and Qx here. Okay. Another way to think about this is in terms of writing this as a conjunction, right? P Alice and P Jabberwock and P Flamingo, and Q Alice and Q Jabberwock and Q Flamingo, and the commutativity and the associativity of the AND operator will let you reorder this thing any way you want. So you can now say P Alice and Q Alice and P Jabberwock and Q Jabberwock and P Flamingo and Q Flamingo. Here is another equivalence. Their x is x Px or their x is x Qx. So what is this saying? Either there is some cell in this first column or there is a cell in the second column that is true, that is lit up. So it's just saying there is some cell somewhere in these two columns that is lit up. What is this one saying? There is some row here such that either Px or Qx, either the first cell or the second cell is lit up. Okay, so again it's saying somewhere in this whole table there is a cell that is lit up. So that's all that both sides are saying. So these are also equivalent. But things get a little tricky if I consider this one here. For all x, px, or for all x, qx. So it's for all, as in the first statement here, but instead of and, I have an or. Okay, and I cannot anymore use just associativity and commutativity of the and operator. It's not ands all over the place. There is an or in the middle. Okay, so this gets a little harder to, it's more tricky to manipulate. If you blindly just took the for all outside and wrote it as for all x, px, or qx, that won't be true. But what you can do is you can start simplifying this by substituting x with a y. Okay, so the variables don't, within their scope, you can rename the variable anything you want, doesn't change the meaning of the expression. So I can just say for all x, px, or for all y, qy. Okay, so nothing has changed. This just second x, within its scope, I changed it to y. Okay, but why did I want to do that? Now, if you look at so what does this look like? So this for all y, qy is just something that is independent of x, right? You could think of it like as an r. So this is saying for all x, px, or r. Okay, for all x, px, or r, and we know that can be written as for all x, px, or r. Sorry, that is this side. For all x, px, or r. I can rewrite it as for all x, px, or r. Okay, so that's what I've done here. I made it px or r. Now I can do this again with respect to y. So what does, and now I think of this px as r, and which is independent of y. I'm thinking of y as my variable. So some expression y for all y, qy. So that's like for all x, px, or r. So this px now is, instead of that, I have an expression that's independent of the variable of interest. So for all y, qy, or r, I can rewrite it as for all y, qy, or r. Okay, so r happens to be px here. So I get, second expression I can rewrite in this way. Well, this is just, for all, the convention, what is written below is exactly saying the statement above, just above that. So the last statement, for all x, for all y, px or qy. Okay, so that's what I can rewrite this as. I can rewrite this for all x, px, or for all x, qx as, so this is this for all and this is or, right? So they are not of the same type, but I can rewrite it as for all x, y, px, or qy. And if you think about this, this is what distributive property will do. You get all pairs, px, qy, so in this case px or qy, and they're all combined together using the AND operator. Okay, and there is an analogous expression for their x's combined with AND. Again, you use two different variables, and you can say px and qy. Their x is x, y, x comma y, such that px and qy hold.